So in the last couple videos, we've learned about this thing called the definite integral. And really, what we've been trying to figure out is how much area there is underneath some curve between two given x values. And we learned that the way we're going to write that is using this notation, this definite integral notation. And what we've done is we've actually calculated some definite integrals and learned some interesting properties of definite integrals by taking advantage of some geometric facts. The fact that we know how to figure out the area of a rectangle and the area of a triangle allowed us to figure out these areas in red and green and pink and whatever this is. And so far it's all been fairly manageable, hopefully for you, but turns out that things are going to get a little bit more difficult, and that's probably not a surprise since this is a calculus class. The challenge of this video is sometimes the curve that we want to know the area underneath is, well, curved. We've only dealt with cases where we've been examining the area underneath straight lines, which conveniently formed rectangles and triangles that we have formulas to figure out the area for. But what about this definite integral here? What if you're interested in finding the area from 0 to 4? So here's where x equals 0, and here's where x equals 4, under the curve 3 minus 1/4 x squared. So that's all this shaded area here, but remember, since this area lies beneath the x-axis, we kind of subtract out this area. We count this as negative area, this is positive area, the net area is what we're looking for here. So how are we going to figure that out? Well, generally figuring this out is going to be the crux of Calculus 2. We're going to spend a lot of time figuring out the area underneath various curves because we don't have formulas for the area underneath parabolas like you see here or any other arbitrary curve. So for now, rather than try to calculate this thing, all we're going to do is estimate the area under the curve. And how can we do that? Well, we kind of have these squares here. This is a 1 by 1 square pictured in pink. So the area of this square is exactly 1. And we got another square here. So now my area is up to 2. It's up to 3, 4, and almost 5 there, huh? We lose a little bit of area right here. So I don't know, maybe we'll count this as a hole, a hole, a hole, a hole, and how much is this? I don't know, like 0.9 maybe? And then what about this one? It looks to me to be, I don't know, roughly half. Maybe we call this one 0.5. And again, I'm just ballparking all of these. This one right here, I mean, we almost get one. We're just slightly short. Maybe 0.9 is appropriate again for this little area. What about this area? I don't know. It looks to me to be a little bit less than half. Maybe I'll call that 0.4 just to throw numbers around. And then finally, this guy is pretty small. I don't know. Is it like a fifth? Maybe. Let's call it 0.2. Okay, and then what about this area in red? Well, to me, the area in red looks a little bit bigger than what we just called 0.2. So maybe we call it 0.3. But remember, because it's below the x-axis, we want it to be negative. So we'll count this area as maybe negative 0.3. I don't know if these estimates were that good. I didn't measure them beforehand or anything. I'm just totally ballparking this to get some idea of how much area there is underneath this curve. Let's see, we got 1, 2, 3, 4, almost 5. This gets us up to 5.3, 5.8, 6.0. I think that worked out really nicely. Oh, but I think I skipped this 0.9. We're up to 6.9 maybe. And then if you subtract this 0.3, I believe the net area is roughly 6.6. Maybe a quicker way to do that is we almost get 6 from 1, 2, 3, 4, 5, and 6, but we're 0.2 short. This makes up that 0.2. And then we got 0.9 more than 6, but we're getting rid of 0.3, so we're at 6.6. If I had to ballpark this area really quick, I'd estimate it to be about 6.6. And if that leaves you very unsatisfied, good. This is a math class. We shouldn't be ballparking things like that. You might take exception. How'd you know this was 0.4? I would have called this 0.3 or whatever. Good. If you have problems with all of that, that's fantastic. Really, if you have problems with this, probably what you need is a more precise way to figure out the area underneath the curve. And we're going to get there, but before we get there, we're going to get a more precise way to estimate the area under the curve. Not because we necessarily care that much about estimates, but because the way we're going to calculate the area exactly is by using the method that we develop by coming up with estimates. So we're estimating not for the sake of the estimate, but for the sake of the method that will later give us an exact result. And I know that's kind of strange, but stick with me. Doing this just kind of ballpark counting up squares got us about 6.6. But maybe a better way to do this is using left endpoint rectangles. What am I talking about left endpoint rectangles? Well, remember, we want the area from 0 to 4. Here's where x equals 0, and here is where x equals 4. So the horizontal distance that I want to cover with my rectangles is 4, right? It goes from 0 to 4. And because I'm going to put exactly 4 rectangles in there, it makes sense that the width of each rectangle will be exactly 1 in order for them to fit in there. So the first rectangle that I'm going to draw is going to go from 0 to 1 here, and then have some height that I need to figure out later. The next rectangle is going to go from 1 to 2, and it's going to have some height that I need to figure out later. The next rectangle will go from 2 to 3, and again, I'll figure out its height in a little bit, and then finally the last rectangle will go from 3 to 4. Okay, so what should the height of these rectangles be? Well, because I'm using left endpoints, what I want to do is look at the left endpoint of each rectangle. So this first pink rectangle goes from 0 to 1. Its right endpoint is 1. Its left endpoint is 0. So to figure out the height of my first rectangle, I look for the height of the curve at the left endpoint at 0. So my left rectangle is going to go all the way up here to 3, because the height of this curve in red, when x equals 0, is 3. Here is my first rectangle. The nice thing about this rectangle is I can figure out the area of the rectangle really easily, right? I can't figure out the area underneath the curve really easily because I don't have a formula for the area of this curved shape. But I do have a formula for the area of a rectangle. It's just the length of the base times the height, if you want to think about it that way. So since this is 3 by 1, the area is exactly 3. What about my next rectangle, the rectangle in green? Well, again, I want to use its left endpoint to figure out the height. It goes from 1 to 2, so the left endpoint is at 1. So the height of the rectangle will be determined by the height of the curve when x equals 1, this point right here. I'm not exactly sure what that is. I mean, I can kind of ballpark it by looking at the graph. I mean, it looks like some number between 2 and 3. I don't know, maybe like 2.75 or something. I'm not exactly sure what it is. Well, good news, you don't have to ballpark it. There's a way to figure it out exactly, and I'll show you in just a second. But first, I want to draw some more rectangles. My next rectangle here goes from 2 to 3. The left endpoint is 2, so I determine the height of the rectangle by looking at the height of the curve at 2 right here, which appears to be 2, although we can confirm that using a method that I'll show you once I'm done drawing all these beautiful rectangles. And finally, my last rectangle goes from 3 to 4. Its left endpoint is at 3. The height of the curve at 3 is, I don't know, something like this. Some number between 0 and 1. Looks like it's about, I don't know, 3/4, give or take. Good news, don't have to ballpark it. You can calculate it exactly. If I could figure out the area of each of these 4 rectangles, I could add up those areas and use that to ballpark the area underneath the curve. And you might have a problem with that. You might be like, it's not a very good estimate, right? Like, look at this red rectangle. There's way more area in the red rectangle than there is underneath the curve. You get all this extra area up here. And it's even worse over here with the blue rectangle. The blue rectangle, part of it's above the curve, part of it's below the curve. This should net out to be negative area, but the blue rectangle is going to give me positive area. Yes, that's all true, but it's okay. It's okay that this is a poor estimate. We just need an algorithm that gives us a consistent estimate. We'll learn later how to make this estimate better and better. For now, we don't care about how accurate the estimate is. We just care about the method of estimation. So what we need to do is figure out the area of these 4 rectangles. The first rectangle, we could tell it's 3 because the height of this rectangle is 3 and the length is 1. The second rectangle in green, we struggle to figure out its area because we can't tell what the height of the rectangle is. Yeah, we can, because we know the equation of this curve, right? It's 3 minus 1/4 x squared. So to figure out the height of this green rectangle, we just need to know what is the height of the curve at 1, because that's the left endpoint of the green rectangle. We just need to evaluate f of 1. F of 1 is 3 minus 1/4 times 1 squared. In other words, 3 minus 1/4. In other words, 12/4 minus 1/4. In other words, 11/4. So the height of this rectangle is 11/4, and the length of the rectangle is 1. So the area of the rectangle is 11/4 times 1, or 11/4. We can do that same thing to figure out the area of the red rectangle. The area of the red rectangle is the length of the base of the red rectangle times the height of the red rectangle. What's the height of the red rectangle? Well, it's just f of 2. Why is it f of 2? Because I'm using left endpoints, and the left endpoint of this rectangle is at 2. To figure out the height of the function at 2, we evaluate f of 2 by copying what we see here, except changing all the x's into 2's. So it's 3 minus 1/4 times 2 squared. 2 squared is 4. 1/4 times 4 is just 1, so it's 3 minus 1. In other words, 2. oh yeah, that's kind of what it looks like on the graph. It looks like it has a height of 2, but now we don't have to trust our eyes. We can actually calculate it and get exact values. 2 times 1 yields a rectangle whose area is 2, which brings me to this last rectangle, the one in blue here. At this point, you can probably see what's going on. I already know the length of the base is 1. To figure out the height of this rectangle, I have to evaluate f of 3, because 3 is the left endpoint of this rectangle. F of 3 is 3 minus 1/4 times 3 squared. In other words, 3 minus 9/4. In other words, 12/4 minus 9/4, which is exactly 3/4. The height is 3/4, the length is 1, the area is 3/4 times 1, in other words, 3/4. I could estimate the area underneath this curve in red by adding up these 4 areas. 3 plus 2 plus 3/4 plus 11/4. So I get 5 plus another 14/4. And for 5 plus 14/4, I can reduce this fraction and make it 7/2. And I can call this 10/2. And 10/2 plus 7/2 gives me 17/2. In other words, 8.5. The approximate area underneath this curve is 8.5. You're like, no, it's not. It's really close to 6.6. Okay, that's true. This is a better estimate than this is, in that this gives us closer to the actual value than this does. But it'll turn out that this estimate is much more useful for coming up with the exact area underneath the curve. But for now, don't worry about it. You will not need to do what you see up here. You will need to do what you see down here. Estimate the area using some number of rectangles. And those rectangles can be left endpoint rectangles like you see pictured here, or they can be right endpoint rectangles like we'll see in the next example. Before I move on to that next example, I want to make one comment. This curve is always decreasing on the bounds that we're looking at from 0 to 4. From 0 to 4, this curve is always going down. What that means, if your curve is decreasing, is that anytime you use left endpoints to estimate the area, your estimate is going to overestimate the true area that is underneath the curve. And that kind of makes sense, right? Because if the curve is going down, then the left endpoint of the rectangle is going to be higher than any point on the curve in that region. So the area underneath that rectangle formed by the left endpoint is going to be greater than the area underneath the curve. So an important fact is, anytime your curve is strictly decreasing on the area that we're looking at, from 0 to 4 in this case, left endpoint estimation will overestimate the true area. And maybe you can imagine if the curve was increasing and we used left endpoint estimation, they'd underestimate the true area. Because, loosely speaking, your rectangles would look something like this, depending on how wide they were. And since I'm using the left endpoint of each rectangle to figure out the height of the rectangle, and the curve is increasing, the curve is always going to be greater than the height of the rectangle, which means that the rectangles are going to miss some area and they're going to underestimate the true value. Let's do this estimation one more time, but instead of using left endpoints, let's use right endpoints. We're again going to go from 0 to 4 to kind of keep the numbers as nice as possible. And we're again going to choose 4 of these rectangles to do, again, just for simplicity's sake. The big thing that changes is now we're using right endpoints. So our first rectangle is still going to go from 0 to 1, but instead of figuring out the height of this rectangle by figuring out the height of the curve at 0, we're going to figure out the height of this rectangle by figuring out the height of the curve at 1. Our first rectangle will now be this one instead of this one, because we're basing the height on this point instead of basing it on this point. And I can do the same thing for the rest of the rectangles. The next rectangle is going to go from 1 to 2. The right endpoint is 2, so I'm going to figure out the height of this rectangle by looking at the height of the curve at 2, and that gives me the rectangle pictured in green. For my third rectangle, I'm going from 2 to 3. I'm figuring out the height by looking at the right endpoint, so the height at 3, and I get a rectangle that kind of sort of looks like this. The fourth rectangle, things get kind of interesting, because my rectangle is going to go from 3 to 4, but the right endpoint is 4. So I need to figure out the height of this rectangle by thinking about the height of the curve at 4. Well, the height of the curve at 4 is a negative number. It's down here. So my fourth rectangle is going to have negative area. It's going to be down below my x-axis. And you know what? That's totally fine. I'll figure out the areas of these 4 rectangles. I'll count this one as negative and these as positive. I'll add up those areas, and that'll estimate the area underneath the curve. Again, much like we saw up here, it's not going to be a great estimate, but it's going to be a predictable estimate for the area underneath the curve. For this first rectangle, I need the height when the function is equal to 1. So I need to know f of 1. Oh, conveniently, I already figured that out. It was the height of this green rectangle, right? This pink rectangle here has the same height as this green rectangle here because the left endpoint from 1 to 2 is the same as the right endpoint from 0 to 1. So in the same way that this rectangle had an area of 11/4, this rectangle has an area of 11/4. And in the same way that this rectangle has an area of 2, this rectangle has an area of 2. Similarly, the height of this blue rectangle was based on the height of the curve at 3, and the height of this rectangle is based on the height of the curve at 3. The height of the curve at 3 is equal to 3/4, so the area of this red rectangle right here is 3/4. Finally, to figure out the height of this blue rectangle, well, the right endpoint is 4, so I need to know what f of 4 is equal to. Remember that f of x is 3 minus 1/4 x squared. So f of 4 is 3 minus 1/4 times 4 squared. Well, 4 squared is 16, and a quarter of 16 is 4. So this is 3 minus 4. This is -1. Oh yeah, that's what it looks like in the picture here. Or at least pretty close, because I don't always draw these super neatly. Maybe now it's better? I don't know. Anyways, the area of this rectangle, it's actually a square, and it has an area of -1. If I were using right endpoint rectangle approximation to figure out the area underneath the curve, what I would have to do is add up 11/4 and 2 and 3/4 and -1. Let's see, 2 and -1 gives me 1, and 11/4 and 3/4 gives me 14/4, which is the same as 7/2. If I think about this 1 as 2/2, 1 plus 7/2 is 9/2. In other words, 4.5. Estimating the area underneath this curve using 4 right endpoint rectangles to approximate the area, I get an area of 4.5. Remember that up here we ballparked the area to be equal to 6.6. And now that I'm using these new methods, which I claim will be much more useful, we're getting these areas that are very different, 8.5 and 4.5. But there's some nice properties of these areas. We know that 8.5 must be an overestimation because this curve is decreasing from 0 to 4. And we know that 4.5 must be an underestimation because the curve is decreasing from 0 to 4. When you're using right endpoints and the curve is decreasing, the area that you get will always be an underestimation. We're always going to be missing some area in here because the heights of the rectangles will be less than the heights of the curve over those intervals. So I still don't know the true value of the area underneath the curve. I suspect it's something close to 6.6, but I don't know exactly what it is. But I know that it's bounded by 8.5 and 4.5. And that's really important. The integral from 0 to 4 of 3 minus 1/4 x squared dx, the area underneath this curve, is still unknown at this point in the class, but it's greater than 4.5 and it's less than 8.5. And it turns out that often it's more important to bound estimates than it is to come up with close estimates. This 6.6 is pretty close, but I don't know if the real answer is a little more than 6.6 or a little less than 6.6. But I do know that the real answer is between 4.5 and 8.5. You're probably a little frustrated at this point. You're like, great, you can estimate the area underneath the curve using this new method, but you get these answers that are not all that close. Well, don't worry. There's a way that we can make these estimates as close as we want to the true value. In fact, there's a way to use these estimates to calculate, not estimate, calculate the true value of the area underneath the curve. And to show you how that works, I want to do one more example. One more example. It doesn't matter if I use left endpoints or right endpoints. I'm just going to pick one. I'll do left endpoints, but really it makes no difference at all. The key thing that's happening in this example is we're going to use 8 rectangles instead of using 4 rectangles. We're still going from 0 to 4, so same region we were covering before, but now we're not trying to squeeze 4 rectangles in here, we're trying to squeeze 8 rectangles in. So I'm covering a horizontal distance of 4 with 8 rectangles. That means each rectangle must have a width of 1/2. So the first rectangle goes from 0 to 1/2, kind of pictured here. I'm going to run out of colors, but I'll let it go for a little while. The second rectangle goes from 1/2 over to 1. The third rectangle is going to go from 1 to 1/2, and so on. I went deep into my color palette to pull out 8 different colors to kind of depict the 8 different rectangles that we're going to use to estimate the area underneath this curve from 0 to 4. The width of each of these rectangles is 1/2 because I'm covering a horizontal distance of 4 with 8 rectangles of equal width. How tall should each of the rectangles be? Well, I'm using left endpoints. So this first rectangle from 0 to 1/2 will use its left endpoint at 0 to figure out its height. The next rectangle goes from 1/2 to 1. The right endpoint is 1. The left endpoint is 1/2. We're using left endpoints, so its height is based upon the height of this curve when x equals 1/2. Same logic for the next rectangle, which goes from 1 to 1.5. Right endpoint's 1.5. Left endpoint is 1. I'm using left endpoint, so I care about the height at 1. And so on and so on. I can draw the rest of these rectangles, in each case using the left endpoint to determine the various heights. In this last one, I think the left endpoint was ever so slightly negative, so this area is ever so slightly negative. I add up the areas of all 8 of these rectangles, and that gives me yet another estimation for the area underneath the curve. Because I'm again using left endpoints, like I did up in this case, I'm going to have an overestimation for the area underneath this decreasing curve. But the important fact is, since I increase the number of rectangles that I'm using, comparing this example to this example up here, I'm going to get a more precise estimate. All right, look at how much extra area we have in these rectangles that's not underneath the curve. And then compare that with this example. There's much less extra area in each of these rectangles that does not lie underneath the curve. We still have an overestimation, but it's not nearly as bad. So all we have to do is go through and calculate the area of each of these rectangles. This first rectangle, we're using its left endpoint. Its left endpoint is 0. The height of the curve at 0 is 3. You might think that that makes the area of this rectangle 3, but it does not, because the width of this rectangle is only 1/2. So a rectangle whose width is 1/2 and whose height is 3 has an area of 3/2. To figure out the area of this second rectangle, its left endpoint is 1/2. So I have to put 1/2 into my function. So I get 3 minus 1/4 times 1/2 squared. 1/2 squared is a fourth. 1/4 times a fourth is 1/16. So I get 3 minus 1/16. 3 is 48/16. So 48/16 minus 1/16 is 47/16. But be careful, that's not the area of this rectangle in red. That's the height of this rectangle in red. The area of this rectangle in red is the height times the length. The length is 1/2. So 47/16 times 1/2 gives me 47/32. That's probably sufficient to illustrate this algorithm, but I'm going to do one more just to make sure you get the point. This rectangle in green goes from 1 to 1.5, in other words, 3/2. I'm using left endpoints, so I'm using the height at 1. I need to know f of 1. We've already calculated f of 1 above. F of 1 was equal to 11/4. So the height of this rectangle in green is 11/4, and the area of this rectangle in green is 11/8. And so continuing in that fashion until I get all the way down to this last rectangle. To figure out the height of this last rectangle, I look at its left endpoint. Its left endpoint is at 3.5 here. In other words, 7/2. So I figure out the height of the curve at 7/2 by taking 3, in other words, 48/16, and subtracting 1/4 times 7/2 squared. 7/2 squared is 49/4, and 1/4 times 49/4 is 49/16. 48/16 minus 49/16 is negative 1/16. Oh, right, the curve is slightly below the x-axis when the x value is 3.5. So the height of this last rectangle is negative 1/6, and therefore the area of this last rectangle is negative 1/32, if you allow me to talk about negative areas, because we're below the x-axis. So something weird happened at the end of the last video, and the last little bit kind of cut off. I don't know, maybe my program knew that it was too long and I should not be making the videos this long and students were done with me, but I just want to finish up the example that we were working on. When I left off, we had figured out the area of each of these different 8 rectangles, which was really close to the finish line. Really, our goal was to estimate the area underneath the curve by calculating the area of each of these 8 rectangles and adding those up. The one thing that got cut off in the video was the adding them up process. So all that I had left to do was to take these 8 different numbers and add them all up. And when I did that, apparently I got 61 over 8. In other words, 7 and 5/8. And the important realization about 7 and 5/8 is that it's less than 8.5. Wait, what was that 8.5 again? Remember, 8.5 was the estimate that we got when we had 4 left endpoint rectangles. This was an overestimation of the true value. The whole purpose of this last example, where we have 8 left endpoint rectangles, is to show how when you use more rectangles, you get a better estimate. 7 and 5/8 is closer to the true value than 8.5 is. It's still not all that close. The true value is going to end up being 6 2/3, I think. But at this point, we're not super concerned with coming up with the true value from an estimate. We're more concerned with learning how, if we have more and more rectangles jammed in here, our estimations are going to get us closer and closer to the true value of the area underneath the curve. And importantly, we don't have to stop with 8 rectangles. There's no reason you couldn't do this again for 12 or 16 or 100 or a million or whatever. And I guess that's a bit of a lie. There is a reason you wouldn't want to do this with 100 rectangles, because it would take you forever. But maybe you can imagine setting up an algorithm where a computer could figure this out for 100 rectangles. And we'll actually get into that a little bit in the next video. But for this video, I want to call this good.